Hello, Black Mountain Chemistry students. Today we're going to learn about acid-base chemistry. I hope this video finds you all doing well and staying safe. And this is going to be chapter 20 in your textbook, so you can feel free to follow along and read the chapter if you have any questions, or email me. But today we're going to look at acids and bases. So in chapter 10 we kind of looked at what acids and bases were. We learned that an acid generally was something that we put into water. So we had the acid, we added water to it, or we added it to water rather, and we formed H plus or H3O plus. And these are the same thing. A base, we learned, was something we added to water, and we ended up with OH minus. Now, we've worked with some of these in laboratory. So, for instance, we have used sodium hydroxide extensively in labs for all the titrations that we've done. Acids that we used include hydrochloric acid, which was the last lab we did, where we did the chemical kinetics lab, and also when we did the titrations of the aspirin, titrations of the aspirin, we use NaOH. The titration that we did last semester, just in general, we use hydrochloric acid and Na and sodium hydroxide here. Other examples of an acid would be vinegar, which has the formula CH3COOH. We used that in the very first lab when we did precipitants and stuff. So what we learned, and when we talked about acids and bases in chapter 10, we learned that acids were something that tended to, taste sour. An example of this would be lemon juice, citric acid, or vinegar. All right, these are both examples of acids that they're at low enough concentrations that, people drink them, in the case of lemonade, or people drink vinegar too and use it for all types of cleaning and stuff. But they tend to taste sour, all right? That is something that is typical of acids. We also learned that bases tended to be bitter, and also they were slippery. So we all got some of the sodium hydroxide on our hands at some point during lab, and you notice that it was very slippery. Ammonia is an example of a base. It is slippery. Most soaps are going to be basic, and they are also slippery, and they taste bitter. So these were the basic tendencies that we learned of acids and bases in chapter 10. So today, though, we're going to talk about three classical definitions of acids and bases. The first one, which is the one that we've already alluded to, is in Arrhenius acid or base. Now, what is an Arrhenius acid or base? An Arrhenius acid or base is something that goes into aqueous solution, which means that we involve water, and we're going to form either H plus or OH minus, okay? And starting with the acid or base on this side. And this is a pretty narrow definition of acids and bases, because there's a lot of acids and bases that take place in other solvents. For instance, there are acids and bases in organic chemistry that take place in ethers or ammonia, where ammonia is also a base, but it also can be a solvent. sometimes. But what this looks like, for instance, an areneous acid, we might have HCl, and then we have over here a water molecule. And what happens here is the electron density is pulled away from the hydrogen, and what that does is it exposes the nucleus of the hydrogen over here and allows these electrons to attack the hydrogen, which then yields this species. Now, we would have a formal charge on the oxygen here, because oxygen, because it is in the 6th period, it would want to have 6 things touching it. But if we look, we have 1, 2, 3, 4, 5 things touching it, which gives it a formal charge of +1, and that formal charge is on the oxygen. Acid's ability to do this is based a lot on the stability of the ion that's going to be left behind, in this case chlorine, which we're going to talk about that more later. The next classic definition of acids and bases is called the Bronsted-Lowry definition. Now here, a Bronsted-Lowry acid or base is going to be something that is going to transfer a proton. So proton transfer. So this is going to be a slightly larger category of acids and bases. And again, HCl is going to fall into this category. If we have HCl here, what we have is we have the donating of a proton to the water molecule, giving us a positively charged water molecule. So the acid is something that creates this. So you can see here that hydrochloric acid is something that falls into the areneous acid, and also the Bronsted-Lowry. So you're going to have acids that show up in multiple categories here. In fact, a lot of them will. Areneous is the most narrow definition because it has to be in water, so it doesn't involve anything like ethers, solvents like ethers and stuff. So, okay, so next we have the Lewis. Why does it do that? All right, next. We have Lewis acids and bases. Okay, so this is going to be the most broad category of acids and bases. So this will also apply to solvents that are water, ethers. Ether would be what's called an aprotic solvent, which means the solvent itself has no protons in it. So the definition of a Lewis acid or base is either going to be an electron pair acceptor, and that would be the acid. Okay, the acid is going to accept an electron pair, and then a donor. So the electron pair donor is going to be the base. So if we look here, we have HCl, and we have water. What we see here is the water is going to be the base in this reaction. So in this particular reaction, we would classify water as a base, and here is the acid. And what's going to happen is this hydrogen is electron deficient because the chlorine is pulling electron density away from it. So what we're going to have here is this oxygen has 2 lone pairs of electrons that are available or to be donated to the hydrogen. And that's exactly what's going to happen, and that's going to give us it's going to give us the hydronium ion again, and that is what H3O is called. Now, this can also happen with other species that you would see and you wouldn't think of being acids. So an example of that would be the reaction of ammonia with boron trifluoride. So here we got NH3, and we got a lone pair on that nitrogen, and then we have boron. Now, it'd be tempting in this case to say, well, let's see, there's hydrogens on the ammonia, so therefore it must be the acid. But actually, it's not. In this case, the nitrogen is a base because the nitrogen has extra electrons that are available for this reaction. And what you have in here is nitrogen would be the electron donor. Therefore, boron would be the electron acceptor. So the species BF3 is the acid and the species NH3 is the base in this case. And then from this, we would get and you'd have a positive formal charge on the nitrogen, and you'd have a negative formal charge on the boron. So this is a Lewis acid and base. It's going to involve the transfer of electrons, and this is the most broad category. All acids and bases fall into a Lewis acid-base category. Okay, so the formation of the species of OH and H plus in water is constant. So we call this the autoprotonation of water. So we can have H2O in naturally there is a equilibrium, which we learned about last chapter, where it forms hydronium and hydroxide ions. Now it's very, very small. The K, and this is called Kw of water, which is the autoionization of water. And this is going to become important later for calculations of pH. But basically, if you multiply the concentrations of these two together, it's going to equal 1.0 times 10 to the negative 14th. So if we add hydronium to water, if we add like hydrochloric acid to water, it's going to form H plus. So we can always divide the concentration of H plus by Kw, which is this number here, to find the concentration of OH in solution. We define a solution to be neutral if the concentrations of H plus is equal to the concentration of OH minus. This would be neutral. We would say a solution is acidic if the concentration of OH plus is less than the concentration of H plus. And what we would have here is, that means we added something that donates the protons to solution. So if you added, let's say, HCl or HI or CH3COOH, that would be something that would increase the concentration of H plus in solution and would make the solution acidic. A basic solution, we would just switch the sign around. So in a basic solution, the concentration of OH will be greater than that of H plus. Now we get this by adding something to the solution that will make it basic. So that could be baking soda, HCO3. That would be a minus if we just wrote it like that. NaOH. Also NaCH3COO. These are our examples of bases, and they're going to contribute to they're either going to add OH minus directly to the solution, or the addition of them to water is going to lead to the formation of OH minus. Now, we have to classify our acids again. So we're going to have something called a strong acid and a weak acid. Now, strong and weak does not mean benign and potent. What we mean by a strong acid is something that dissociates completely into solution. So there is a table 20.1 on page 734 of your book that has the list of all the strong acids. And there's not a whole lot of them. So it's just something you'd have to memorize because there's no way to really figure out what's a strong acid except through experimentation. So your strong acids include HClO4, HNO3, so this is perchloric acid, this is nitric acid, H2SO4, that's sulfuric acid, HCl, HBr, and HI. So hydrochloric acid, hydrobromic acid, hydroiodic acid. Any acid that is not listed here is considered a weak acid. So what this means, all this means is that they dissociate completely. So when you put, for instance, HCl in water, you get 100% products, which the 100% products would be H3O plus Cl minus. Okay, and that's what a strong acid is. So basically, when we learned last chapter, we learned about equilibrium, and we learned that reactions that have a large K value means they have a lot of products and very little reactants. Well, that's exactly what a strong acid is. This is a chemical reaction that is written here on the screen that has a K value. We're going to call it Ka because it's the K of an acid. But the Ka is very, very large, meaning that you're going to essentially end up with 100% products. So a strong acid, to write it on the screen for you, is going to be 100% dissociation into products. Now, the HCl together here is covalently bonded, and then it dissociates here. Okay, so that's the dissociation we're talking about. Okay, so these are the strong acids. Okay, so a weak acid is going to be all other acids, and primarily organic acids. So examples of weak acids include acetic acid, CH3COOH, which is your vinegar. We have HOOCCOOH. This is called oxalic acid. Then we have formic acid, HCOOH. Then there's lactic acid, there's citric acid. Another weak acid is HF. Now this one is interesting because just because it is a weak acid does not mean it is benign. This acid is highly, highly caustic. In the movies, when they want to dissolve bodies in acid to cover up for the crime, this is what they're using here, HF. Very, very dangerous, even though it is considered a weak acid. It does not, these acids do not form 100% products. So if we have our weak acid, which we represent here as HA, H being the acidic proton, A being the rest of the molecule, and we put it in H2O, we still end up with H plus and whatever the conjugate base is, which we're going to get to in a couple minutes. But this is less than 100%. So, and usually much less than 100% dissociation. So, to write on the screen for you, a weak acid is going to have, is going to favor reactants. So it's going to have a small K, whereas the strong acids had a large K. So what makes an acid strong or weak? There's a couple different things. The first one is going to be, the main one is going to be the related to the stability of the anion. So we can draw here a couple acids. So this is sulfuric acid. This is a very strong acid. And here we have hydroiodic acid. These are both strong acids. Now, they're both strong for different reasons. So if we deprotonate the sulfuric acid here, it gives off its proton to a water molecule. You're going to have a negative charge and six lone electrons on that oxygen. Now, this one is strong due to resonance stabilization. As you can see, there are multiple resonance structures that we can draw here. We could move this single bond to this oxygen and move that negative charge to here, and we could move it to this oxygen and move that negative charge out here. And we learned in Lewis structures that resonance structures, all the different resonance structures that we could draw here are all represented in one molecule at the same time. So what you have is you have a delocalization of the negative charge. So what you have is the negative charge, that extra lone electron pair, is dispersed throughout this entire side of the molecule. A rule of physics is that if you can disperse a charge over a larger area, the more stable that species is going to be. And that's exactly what happens in the case of sulfuric acid. This is a relatively large area to disperse a negative charge. Therefore, it's going to be a strong acid. It's going to be stable once it releases that hydrogen. Iodine is also stable as an anion, and that is because it is lower on the periodic table, which means it is a larger molecule. So when this dissociates into H plus and I minus, I minus anion is much more stable than, for instance, fluorine, because it has more shells of electrons. Remember, we learned that atoms were like onions. They had layers of electrons, and the more layers you have, when you have a charge on that atom, is going to be more stable. So fluorine is a weak acid because fluorine is really unstable as an anion. So if we look at the stability or the strength of the halogen acids, we have fluorine, chlorine, bromine, and iodine, and the strengths of the acids are directly related to the stability of the anion. So iodine is stronger than bromine, which is stronger than chlorine, which is much stronger than fluorine. And that's because fluorine, if you remember, is a 2s2 2p5. So it's only got one valence shell, one full valence shell around it. So it's got the 2, and then it's got 2, 3, 4, 5, 6. So it would have less electrons around it, therefore has a smaller diameter, versus iodine, which iodine is all the way down in the, let's see, it would be a 5s2 5p5, or it actually, once it's an anion, it would be a 5p6. So it has more layers of electrons around it, which makes the atom much bigger, which gives you a greater area to disperse that negative charge over the fluorine. And that explains the increasing strength of the halogen acids. So we can use the auto-ionization of water, what we just saw, and the concentration of an acid that we're going to put into solution to find the concentration of all the species in solution. So what that looks like, if you look at practice problem 20.1, I should say, it asks us to find the concentration of H3O plus and OH minus when we make a 0.60 molar solution of HNO3. So first thing we're going to do is we're going to see if HNO3 is a strong acid, which it is. It's on the table 20.1 in your book. It's also on the list I wrote a couple screens ago, which means that if we're going to write our reaction here, HNO3, when we add water to it, we're going to end up with 100% products. Which means that our concentration of H plus is going to be equal to 0.6. Why? Because that's how much we put in there. So if we wanted to now find our concentration of OH minus, well, we remember that Kw is equal to the concentration of H plus multiplied by OH. And we know that Kw has a numerical value to it. It's 1.0 times 10 to the negative 14th. So if we want to find the concentration of OH in the solution after we added that, all we do is take 1.0 times 10 to the negative 14th, divide it by the concentration of the H plus, which would be 0.60, and this is going to be equal to the concentration of OH minus, which in this case is going to be 6.7 times 10 to the negative 14th molar. So really quite small. And in case you missed how we solved for this, well, if Kw is equal to H plus times OH minus, well then OH is equal to Kw divided by H. So therefore we can find the concentration of OH in solution by simply dividing the autoionization constant over the concentration of acid. Now let's talk about bases. We talked about acids, but there are also strong and weak bases. And how do we know what is a base and what is not? So I can write here NaOH, something we've used a lot, and also I can write CH3OH. Now, both of these can be bases. Generally, we can only consider, well, they can both be bases. Only one here is a strong base, and all the strong bases are listed in table 20.1 in your book. But basically, to know if something is a strong base, is it ionically bonded? So if we look NaOH, what that molecule looks like is you have oxygen covalently bonded to hydrogen, and you have a negative formal charge, and then we have the sodium ion oriented near the negatively charged oxygen. This is ionically bonded. So therefore, when we put it in water, it solubilizes and breaks it up and allows you to have the strong base. This is CH3OH. This is an alcohol, methanol to be exact, and it has basic properties. It is definitely a Lewis base. It can also be a Bronsted-Lowry base if you put the right acid in there under the right conditions. But notice this is covalently bonded. So what this molecule would look like here is you'd have the 3 hydrogens around the carbon, then you have the oxygen here, and then the H. Now, this is a covalent bond. You have no formal charges in this molecule. All the species are pretty happy in it. Things are good to go. It's not that reactive in the sense of like the sodium hydroxide would be. So if you're more interested in bases, again, you can look at table 20.1 in your book. There's a list of them there. Basically, it's going to be the group 1 in a lot of the group 2 metals. So the lower level group 2 metals and pretty much all the group 1 metals are going to be strong bases. Okay, so we need to measure, we need to have a way to quantify the acidity or basicity of a solution. And for that, we use the pH scale. Now, the pH scale is a logarithmic scale. And we use it to measure the acidity or basidity of a solution. So, acidity slash of a solution. So it's going to use the log base 10 scale, which means that every number we change is going to be a 10 times difference in the base, whether it's more acidic or basic. So if you remember from the very first homework assignment I ever gave you, I showed you that the log of x is equal to y, so then 10 to the y is equal to x. So what this looks like, if I had log of 1,000, well, that would equal 3. The log of 100 would equal 2. The log of 10 would equal 1. And the log of 1 would equal 0. Likewise, if I take 10 and raise it to the third power, that's equal to 1,000. 10 to the second power is equal to 100. 10 to the first power is equal to 10. And then 10 to the 0 power is equal to 1. Okay, so this is what a log base 10 is. So therefore, if we say something has a pH of 2 or a pH of 1, well, we would say that the thing with the pH of 2 is 10 times more acidic than something with a pH of... The thing with a pH of 1 is 10 times more acidic than the pH of 2. So the equation we use for pH is going to be pH is equal to the opposite of log of the concentration of hydronium in solution. So if we put a strong acid into a solution, you're going to end up with more hydronium, so it'll have a lower pH than, let's say, a weak acid. So we can use this to find different... So the concentration here is going to be in molar. So if I asked you to find the pH of the following HCl solutions, now remember HCl is a strong acid. So let's say we had a 5.0 molar solution, a 0.01 molar, a 0.001 molar, and a 0.25 molar solution. Now we're going to use, it's going to be the opposite of log, because these would be, anything less than 1 would have a negative value, which we don't want. So the formula for pH is the negative log. So if we plugged in negative log of 5, that's equal to negative 0.69. The negative log of 0.01 is equal to 2. Now the actual log of 0.01 is negative 2, but the pH scale goes from 0 to 14. We can have pHs above and below that scale, but generally it's going to be 0 to 14. So we use the opposite log to keep things positive. So then the opposite of log of 0.01 is going to be 3. And then the opposite log of 0.25 is going to be 0.602. So these would be the respective pHs of the solution. Now, it is okay to have negative pHs. This would be a very concentrated solution of acid, so therefore it would have a negative pH. So if given the pH of the solution, we can find the molarity. So using if the log of x is equal to y, then 10 to the y is equal to x. So from that, we can say that the concentration of H plus is equal to 10 to the opposite of pH. So if I was going to ask you to find the concentration of hydrochloric acid in a pH 2 solution, you would just raise it 10 to the negative 2, which would be 0.01. And that's how you can go back and forth between the concentration of the acid and the pH. So here's our scale for acid and base, and here on this side we have acid, on this side we have base. Generally speaking, the scale goes from 14 to 0, and you can have things on the outside on either side, and a negative or a 7 is going to be neutral. So 7 is where in water the amount of OH and H plus are equal to each other. Anything in this area, what you're going to have is OH is greater than H plus. Anything on this side, you're going to have OH is less than H plus. And the more acidic something is, the lower the pH is going to be. So we can use the pH to find the concentration of the base 2 using the auto-ionization of water. So for example, if I asked you to find the pH of the following basic solutions. So we're going to have 0.25 molar NaOH and a 0.15 molar KOH solution. Now, both these happen to be strong bases, which means in solution our concentration of OH is going to be, we'll do the first one, is going to be 0.25 molar. Now the pH is concerned with the concentration of hydrogen, not the concentration of hydroxide. So first we have to use Kw is equal to OH times H plus to find the concentration of H plus. Well, for that, we just do H plus is equal to Kw divided by OH, which for our case is going to be 1 times 10 to the negative 14th divided by 0.25. Plug that into your calculator, you're going to end up with 4.0 times 10 to the negative 14th. Now, that is going to be concentration of H plus. So now to find the pH, we just take the opposite of log of H plus, which is equal to the opposite of log of 4.0 times 10 to the negative 14th, which is going to be equal to 13.4. So as you can see, that's a really basic solution, almost to the top end, almost a 14. I'm sorry about these lines appearing. I don't know why that keeps happening. Okay, so for the second one, there's actually another way we can solve for this. So we can first solve for the POH, which the POH is just going to be equal to the opposite of log of the concentration of OH. So for the second one, it was a 0.15 molar of KOH, which is also a strong base. So the POH is going to be equal to the opposite of log of 0.15, which is equal to 0.82. That would be the POH. Now, pH is always going to be equal to 14 minus POH. And we know this because pH plus POH will always equal 14. So if we solve for pH here, then it's going to be pH is equal to 14 minus POH. So that looks like here is this would be 14 minus 0.82, and that's going to equal 13.2. And that would be your pH of the 0.15 molar solution of KOH. Now, these are high pHs because those were just bases that we used for examples. So, pH scale, just for comparison, so we have an idea of where things lie on the pH scale, which is interesting. Over here we have base, over here we have acid. So some things that lie on the acidic side that you use in your everyday life are vinegar, lemon juice. Vinegar, generally your household vinegar has a pH of 2.5. Lemon juice, generally a pH of 2.1. Soda generally has a pH of around 3.5, which is pretty acidic, which is why soda is so bad for your teeth. Milk is also slightly on the acidic side, so milk generally is about 6.5 your pH. Tap water can range widely, anywhere from about 5.5 to 7.8. Around here, it tends to be more on the basic side because we got a lot of minerals dissolved in there. So when you have salts and stuff dissolved, things tend to become more basic. Human blood is supposed to be a pH of about 7.2. That's healthy. If you have acidic blood, it can't transport oxygen as well, which is why ketoacidosis is such a dangerous condition in the human body. We'll probably talk about that when we get to the biochemistry topics. Your diet can greatly affect the pH of your blood. People that have a poor diet tend to have acidic blood and poorer health because they can't transport oxygen around their bodies easily. Your household detergents, whether it be dish soap, laundry soap, usually are right around the pH 10. And ammonia, so your Windex, is a base, and that's going to be usually around 12. And a lot of people, when they look at ammonia, they see, well, NH3, oh, that must be a acid because it has hydrogens on it. Well, no, that's not the case. It's actually a Lewis base. So we talked about weak acids and how they only partially dissociate in solution. So strong acids dissociate to form products entirely. Weak acids only partially dissociate. So what that looks like, if we have a chemical reaction here, HA and we get H plus A minus. The concentrations of these two products is fairly small compared to the concentration of this in solution. And we're going to have to use what we learned last chapter in equilibrium to find out pHs for these solutions. First thing I want to talk about is every acid has a pKa. The pKa of an acid is equal to the opposite of log of Ka. So if something has, vinegar has, for instance, the pKa of 4.75. Now, which equates to like being 1.8 times 10 to the negative fifth in Ka. So we can't just go around saying, in a textbook, oh yeah, the Ka is 1.8 times 10 to the negative fifth for vinegar. So we take the log of it to make it a more manageable number. So the pKa is a more manageable number. So for vinegar, it would be 4.75. The lower the pKa, the stronger the acid. The larger the pKa, the weaker the acid, and as you get really high, the stronger the base. And each change in one, so if we had a difference between a 4.75 and a 5.75, this is saying that the 4.75 is 10 times more acidic, just like the pH scale. Okay, so last chapter we learned that Ka, or the K equilibrium, is equal to the concentration of products over the concentration of reactants. So that chapter was before this one because we're going to use what we learned in that chapter in this chapter. So now the Ka, which is just the Kc of an acid, is going to be equal to the concentration of H plus times the concentration of A minus, which is the conjugate base, over the entire concentration that was put into solution. So in case you haven't caught on yet what the HA is, so if we had so here's vinegar. Okay, so vinegar is going to form in water H3O plus and CH3C O minus. So this is HA. This is H plus, obviously, and this is A minus. So in our equilibrium constant, we have HA in the bottom. That would be the total amount of this species you put in. Then H plus at the top, these are your products. It would be the concentration of these two, which these two would be equal to each other. So, for example, we're going to find the pH of a 0.8 molar solution of vinegar, and the pKa of vinegar is 4.75. Okay, so the first thing we do is need to find the Ka. So the Ka of vinegar is going to be equal to 10 to the negative of pKa, which in this case will be 10 to the negative 4.75, which is equal to 1.78 times 10 to the negative fifth. That's our Ka. So now we can write our expression. So we found that Ka is going to be equal to H plus times A minus over HA. So what this would look like here is we would have 1.78 times 10 to the negative fifth is equal to the concentration. Now these two are multiplied by each other and they're equal, so we'll just make it x. It'll be x squared because they're multiplied by each other over the concentration of HA, which is going to be which is going to be 0.8 minus x. So you can see here we're going to have to solve the quadratic for this. So first step is going to be multiply both sides by 0.8 minus x, and what that is going to give us, it's going to give us 1.78 times 10 to the negative fifth times 0.80 minus x is equal to x squared. So then in that case 0 is going to be equal to negative x squared minus 1.78 times 10 to the negative fifth x plus 1.42 times 10 to the negative fifth. So now if we solve the quadratic, opposite of b plus or minus the square root of b squared minus 4ac over 2a, and here we have a, which is just going to be 1, right? 1. B and c, when you put that in your calculator, you can get two values, but only one will be positive, and the positive value is 0.0037. Now, this is going to be equal to our concentration of H+. So now, to find the pH, we would just take the opposite of log of our value of our concentration, which is equal to the opposite of log of 0.0037, and that's going to come out to be 2.42. So that would be the pH of a 0.8 molar solution of vinegar. Now, in some cases we can use something called the approximation method, which is going to be a lot easier. And we can do this whenever the Ka of an acid is less than 1 times 10 to the negative fourth. So if we were going to find that pH of that same solution, we look at the Ka. Well, it's 1.78 times 10 to the negative fifth. Well, this is less than 1 times 10 to the negative fourth, because it's 10 to the negative fifth. And we can write our expression here, x squared over 0.8 minus x. Now, because we know that x is going to be very, very small, we can assume, because Ka is so small, that the denominator essentially stays the same. So we can just forget about this x right here. Now when we solve, we can take 1.78 times 10 to the negative fifth multiplied by 0.8 is equal to x squared. Now we can just take the square root of both sides, and what we're going to find is x again is equal to 0.0037, which is equal to the concentration of H+, which, incidentally, we take the opposite of log of that, the pH is equal to 2.42. That is the approximation method. And as you can see, it is a lot easier. So that works because the Ka is so small, we can neglect that x in the denominator and forego solving the quadratic. So we'll do a couple more quick examples. Find the pH. So we're going to find the pH of a 0.25 molar solution of benzoic acid. And the Ka for this one is equal to 6.3 times 10 to the negative fifth. Okay, so because Ka is less than 1 times 10 to the negative fourth, we can use the approximation method here. So if we set up our expression, we can say that 6.3 times 10 to the negative fifth is going to be equal to x squared over 0.25 over 0.25, because we can neglect that minus x. Well, now if we just take 6.3 times 10 to the negative fifth and multiply both sides by 0.25, we're left with this. Now we can take the square root of both sides, and we find that x is going to be equal to 0.0396. Now if we take the opposite of log of 0.0396, we find that the pH is equal to 2.4. And that's our answer for that question. So again, we can use the approximation method here because Ka is very small. All right, last example, and we'll be finished with this lecture. We're going to find the pH of a 0.05 molar solution of chloroacetic acid. And the Ka for this one is equal to 1.4 times 10 to the negative third. Now, unfortunately, this one is 1.4 times 10 to the negative third is greater than 1 times 10 to the negative fourth by a factor of 10. So we're going to have to solve the quadratic for this one. So if Ka is going to be equal to H plus and A minus over HA, set up our expression here. We have 1.4 times 10 to the negative third is equal to x squared over 0.05 minus x. We can multiply both sides by the denominator here, and that's going to give us 1.4 times 10 to the negative third times 0.05 minus x is equal to x squared. If we multiply this in to here, we're going to end up with, and then we set it equal to 0, we're going to end up with is 0 is equal to negative x squared minus 1.4 times 10 to the negative third x plus 7.0 times 10 to the negative fifth. Now we can solve the quadratic, and we're going to find out that x is going to be equal to 7.7 times 10 to the negative third molar, and this is going to be equal to concentration of H plus. Now to find the pH of that, pH is equal to the opposite of log of the concentration of H plus, which is x in this case. So we can say that the pH is equal to the opposite in log of 7.7 times 10 to the negative third, which is going to be equal to 2.11. So the pH of chloroacetic acid of a 0.05 molar solution would be 2.4. All right, and that is going to be it for this lecture.